In the last few lectures, we have been discussing the dual nature of matter, in which we learned that matter can behave sometimes like waves and sometimes like particles. In particular, we found electrons can behave like waves. If they can do, then can we have electron microscope? And we learned that it is possible to have a microscope in which electron waves are used. And this electron microscope has what are known as electromagnetic lenses. And we also learned the principle of a magnetic lens. We have varying magnetic field and we have a source of electrons. When these electrons go through the magnetic field, they get focused at this point. And with the help of the electromagnetic lenses, we could construct an electron microscope. Then we had to talk of the resolving power of a microscope. Resolving power of a microscope depends on what is known as numerical aperture. That means, this angle alpha, the cone that waves exert on this lens, half of that, this angle alpha, is called numerical aperture. So, with the help of numerical aperture, we were able to define the resolving power of a microscope. Now, in the next few lectures, we intend to take up the topic of atomic nucleus. The discovery of atomic nucleus follows the discovery of electrons by Thomson. You remember the cathode rays. Thomson analyzed cathode rays and found that these are actually electrons, negatively charged particles. And since these are parts of all matter, he thought that the atom therefore would consist of electrons and positive charges mixed, so that the overall charge of the atom is nil. That means, the overall atom is neutral, and because of its shape like this, because of its appearance, this came to be known as the plum pudding model. The important thing is that in this atom, the electrons and positive charges, they are mixed uniformly, so that the atom as a whole is neutral. Now, if it is a plum pudding model, then Rutherford reasoned that since the electric field inside is quite weak, you see the field of electrons and protons is cancelled, therefore, the field inside is quite weak, and therefore, Rutherford thought that if I shoot a beam of alpha rays on a target, say a gold foil, then because the atoms are neutral and the electric field inside the atoms is weak, therefore, all these alpha particles will go through with very little deflection. A few of them would be deflected by very small angles. That is what he thought, but when he performed this experiment, that is, he shot alpha rays on a metal foil, he found to his surprise that not only the alpha rays, some of alpha rays suffered large deflections, some of them were even reflected backwards. So, that gave him the idea that the atom is mostly vacuum, mostly empty, so that most of the alpha rays can go through it. At the center of the atom, he thought there must be a part which has all the mass and all the charge of the atom. That is why, because this charge is concentrated, that is why the alpha rays, some of the alpha rays suffered very large deflections. Some of them even got sent back. So, after this, he proposed his own model of the atom. What was that model? That model was, before that, let's see. That model was we have learned that earlier, that like the solar system, that we have the positive charge inside at the center of the atom. This center is known as nucleus and electrons go around it. Now, here I must point out again, we have been doing this occasionally to bring you the glimpses into the working of science. As explained already, each new model or theory must make predictions which can be tested experimentally. This I have told you earlier also, that each theory or new model must make predictions which can be checked experimentally, and if those predictions are found to be correct, then the theory is accepted, otherwise it is rejected or modified. The important thing is that the scientists do not attach their prestige to their theories. However important or well known the scientist may be, the proposed theory must stand the test of experimental verification. If the experimental verification fails, then the theory is rejected, however important that scientist may be. Rutherford's own model, Rutherford, remember, during that time was an extremely important and well known scientist, and his own model of the atom had to be rejected because it was found unstable, whereas observations say that atom is stable. So, even Rutherford, at that time one of the most prestigious scientists, his theory had to be rejected. The observations showed clearly that the electrical charge must be concentrated at the center of the atom, so that a very strong electric field there could deflect alpha rays by large angles. Most of the atom of course is empty, most of the alpha rays go through, but those which pass near the center of the atom, which carries the charge, they get deflected by large angles. At the center of the atom, however, there must be a region of high density which accounted for the mass of the atom. Not only this region has the charge, this region called nucleus also has the mass of the atom, and around the nucleus were orbiting clouds of electrons. But what was the nature of the nucleus, apart from the fact that it contained the whole mass and charge of the atom? Rutherford decided to investigate this matter by shooting alpha particles on lighter nuclei like lithium, beryllium, boron, carbon, etc. He found that when he shot alpha particles on the nitrogen nuclei, hydrogen nuclei were emitted by them. You see, you have nitrogen and you shoot alpha particles on the nitrogen particles, you found that the nuclei of hydrogen atoms were emitted. He concluded, and correctly, that the hydrogen nuclei came from inside the nitrogen nuclei. He called the hydrogen nuclei as protons. So, we have nitrogen target, alpha particles are shot and then protons come out. That is what he found. Since the atom had to be neutral, the proton had to carry exactly the same charge as electron. Electron and proton carry exactly the same charge. Why? Because otherwise the atom would not be neutral. So, you have proton, say in hydrogen atom there is one electron. So, the charge of the two must be exactly equal and opposite. So, that hydrogen atom as a whole is neutral. So, it was found that the mass of the nucleus, which carries the positive charge, mass of the nucleus is about 2000 times the mass of the electron. So, what picture do we have now? We have an atom which is mostly empty. At the center of the atom is nucleus which carries positive charge, and around this nucleus are electrons which are orbiting around this nucleus. That is the picture of the atom we have got. But what is nucleus? What are its constituents? That became then a very important question. Rutherford suggested that all nuclei consisted of protons. However, there was a problem. What was the problem? The next atom next to hydrogen, helium, has the mass equal to 4 times the mass of hydrogen. That means, there must be 4 protons, or must be particles which have the mass of 4 protons. But the atom of helium carries only 2 electrons. So, how do you make the atom neutral? if the nucleus carries 4 protons and there are only 2 electrons going around it, then you cannot make the atom neutral. So, what did Rutherford do? He said, all right, he suggested that 1 proton and 1 electron inside the nucleus, they form a sort of a group which nullify their charges. So, that only 2 charges are left, that is 2 protons are left, and that is how we explained the charge of the nucleus of helium. However, this created another problem. What was that? How could electrons exist inside the nucleus? Let us see whether they can or cannot. De Broglie principle says that each particle of momentum p has a wave associated with it, the wavelength being given by lambda equal to h by p. This relation is now familiar to you, de Broglie principle. So, lambda is h by p. The reason why we do not appreciate the wavelength associated with ordinary objects is that the wavelength is extremely small. You remember the exercise that we carried. We had a cricket ball moving with a speed of 150 kilometers per hour. We found its wavelength is extremely small. So, you can't appreciate it. Now, if the electron exists inside the nucleus, then its wavelength at most could be equal to the diameter of the atom. And if we assume the diameter of the atom to be 6.6 into 10 to the power minus 15 meters, that is 6.6 Fermis, then the wavelength of the electron, which is equal to the diameter of the nucleus, would be 6.6 Fermis. If that is the wavelength, we can find the momentum from the de Broglie principle, and we find that the momentum is equal to 10 to the power minus 19 kilogram meter per second. And from this momentum, we can find the energy. You know, the formula for the energy of the electron is the square root of p squared c squared plus m c squared whole square, which is effectively equal to p c in fact. So, from this momentum, we can find the energy of the electron, and you can see this energy is a few hundred MeV. And if we did this exercise with protons, their energy would be only a few MeV. The energy of the electron is a few hundred MeV, and this energy is large, very large compared with the energy involved in nuclear processes. I mean, nuclei emit particles and energy, but that energy is much smaller than the energy that we have calculated for the electron. There is another argument. If the electron exists on the surface of the nucleus, then its potential energy would be minus 1 by 4 pi epsilon 0 q 1 q 2 by r, where r is the now radius of the nucleus, and we can calculate this, and we find that this energy is 10 to the power minus 13 joules. Now, this energy we found earlier, 3 10 to the power minus 11 joules, is much larger than the energy for the electron at the surface of the nucleus. This means what? This means that the nucleus cannot hold electron inside it. Electron energy is much higher than the energy of the electron on the surface of the nucleus. That means, the potential barrier for the electron to escape is much smaller than its own energy, and therefore, it can escape. So, electrons cannot exist inside the nucleus. So, if electrons cannot exist inside nucleus, what do we do? There is another argument based on what is known as Heisenberg's uncertainty principle, which we shall study in a few more slides down the line. We shall study this argument. Here, the uncertainty principle says that the product of the uncertainty in the location of an object and uncertainty in its momentum, the product of these two is equal to h cross. That is, the uncertainty in the momentum is equal to h cross by delta x. Delta x is the uncertainty in the location, in the position of the particle, that is delta x times delta p is equal to h cross. H cross, you remember, is h by 2 pi, where h is Planck's constant. So, this uncertainty principle also told us that the electrons cannot exist inside the nucleus. So, now what happens to the argument suggested by Rutherford, that one electron and one proton can form a pair which is neutral. If electrons cannot exist, this obviously cannot happen. One of the important objections to the existence of electrons inside the nucleus was the uncertainty principle of Heisenberg. This uncertainty principle says that the uncertainty in the momentum of a particle multiplied by the uncertainty in the position of a particle, their product is equal to h cross, where h cross is h by 2 pi and h is Planck's constant. That is, the uncertainty in momentum of the particle delta p is h cross by delta x. Now, it was this uncertainty principle which disallowed the existence of electrons in the nucleus. For the time being, let us stop or interrupt this story of the nucleus. Let us pay attention to the uncertainty principle, which is a very important principle of physics. In 1927, Heisenberg was working on the implications of the new discovered discipline of quantum mechanics. You remember, quantum mechanics came into existence only in the early 20th century. Bohr's model was 1908 or something, and that is said to be the beginning of quantum mechanics. Anyway, so this was a new subject and it was being developed very fast, in fact, and Heisenberg was one of the scientists who was doing this work. And during this work, he found that he discovered, in fact, that the momentum and position of a particle cannot be known precisely at the same time. That is, if you know precisely or very little uncertainty the position of the particle, then its momentum is highly uncertain. On the other hand, if you know the momentum with little uncertainty, then its position becomes highly uncertain. That is what he discovered, and he said this is not due to any limitation of the experimenter or the equipment or any shortcoming in the technique. He said this is inherent to quantum mechanics. However precise the experiments may be, however well versed the scientist may be doing the experiment, whatever the techniques he applies, he said the uncertainty does not depend on that. Uncertainty is inherent to quantum mechanics. How can we explain this? You remember, we discussed this earlier, that a particle when it moves has associated with it a wave, a group of waves, as shown here again. As the particle moves, it moves along with the group of waves. Now, the particle can be anywhere in this group of waves, and we also found that if the particle has larger velocity, then the group of waves has a smaller extent. So, let us try to explain the uncertainty principle on this picture, that a particle has a wave associated with it, or a wave group of waves associated with it. So, I show you once again this particle along with the wave group. This wave group consists of several waves. I have just shown 4, but it consists of several waves. All these waves combine to form this wave group, and the particle is somewhere inside this wave group. So, therefore, one can say that the extent of this wave group is the uncertainty in the position of the particle, that is delta x. Therefore, the spread of wave packet is the uncertainty in the position of the particle. Recall that each wave carries a momentum with it. Again the de Broglie principle, h is lambda by p. So, lambda is h by p. So, each wave has momentum associated with it. Now, let us see what happens. Suppose we wish to reduce the uncertainty in the position of the particle. Let us say we want to reduce this uncertainty. How can we do that? By making this group have a small spread, by reducing the spread of this wave group. If we do that, then we need larger number of waves to constitute this group, and larger number of waves means larger uncertainty in momentum. So, as we restrict the uncertainty in the position, the uncertainty in the momentum becomes large. Let us do the opposite now. Let us try to restrict the uncertainty in momentum and see what happens to the uncertainty in the position. In the extreme case, let us have only one wave, so that we know its momentum precisely. So, if we have just one wave, then what is the uncertainty in the position? Uncertainty in the position becomes infinite, because this wave is infinite. So, if we try to reduce momentum, the uncertainty in momentum, we have large uncertainty in position. On the other hand, if we try to restrict the uncertainty in position, we have large number of waves to constitute this group, and therefore, larger uncertainty in the momentum of the particle. So, you can see that you cannot reduce delta x to 0, because if you do that, then delta p becomes infinite. You cannot reduce delta p to 0, because delta x becomes infinite. That means, it is not possible at the same time to know precisely the position and momentum of a particle. This is the Heisenberg's principle of uncertainty. Thus, whatever we do, the uncertainties in both variables, position and momentum, cannot be simultaneously removed. According to Heisenberg, the product of the two uncertainties is given by delta x times delta p equal to h cross. Let me warn you, some books say that delta x by delta p is equal to h cross by 2. Nothing wrong with that, because delta x by delta p is actually the upper limit on the upper limit. In fact, h cross, let us say put the other way around, h cross is the lower limit on the product delta x delta p. So, it does not matter whether this lower limit is h or h by 2, it does not matter, but some books say delta x into delta p is h cross, some books would say delta x into delta p is h cross by 2. So, you be aware of that, so that when you have to solve numerical problems, you must be aware what you are doing. The position and momentum variables are called complementarity pair in quantum mechanics. Another such pair is energy and time. So, that delta E times delta t, that is uncertainty in energy multiplied by uncertainty in time, that is also equal to h cross. It was thought earlier, in fact, Heisenberg himself seems to suggest so, that the process of measurement of say the position of a particle disturbs the system, and therefore, there is uncertainty in the momentum. Now, new experiments have shown in very recent times, in the last 10-15 years, the experiments have shown that even very delicate experiments, where when you measure the position of the particle, you do not disturb the particle at all or disturb it extremely little, even then there is uncertainty in the momentum of the particle. So, one must conclude that this uncertainty is inherent to quantum mechanics. It cannot be, even very delicate experiments cannot reduce delta x and delta p at the same time, cannot determine position and momentum precisely at the same time. So, this uncertainty is actually what you may call fuzziness in the knowledge of complementarity pairs, that is position, momentum, energy, time. is inherent in quantum mechanics. So, in this lecture we studied the development leading up to the discovery of the nucleus, and we were discussing the nature of or the structure of the nucleus. When we interrupted this story to understand the uncertainty principle, which makes impossible for the electrons to exist inside the nucleus. In the next lecture, we shall see what uncertainty does to the Bohr model, and we can then resume our story of the structure of the nucleus. We shall study the discovery of neutron, strong nuclear force, absorption of neutron by nuclei, etc., etc. Then we shall at the end learn about fission by neutron capture. That is in the next lecture.